All right, so here we are with part 2 of the review for exam number 2, or the review of exam number 2. In this, I'm going through questions number 6 to, I believe, 13. So go ahead and pay attention. So question number 6 reads, which of the following amino acids is considered a secondary structure breaker? Okay, so this ultimately has to do with which amino acids are likely to be found in a secondary structural element and which are not. So it's important to kind of review alpha helices versus beta sheets. And go ahead and take a look at, what does an alpha helix look like? What does a beta sheet look like? Where are the R groups and everything like that? This ultimately is a sort of discrete question. The answer to this one is glycine. And the reason that it's glycine is because glycine is a very small amino acid and it's fairly flexible. And so the issue is that it's entirely too flexible. So C, glycine, is the correct answer for this one. Okay, this question looks a little bit wordy and overwhelming, but let's go ahead and read through it. Experiments on denaturation and renaturation in the enzyme ribonuclease A by Dr. Anfinsen have shown that, okay, so whenever you're confronted this question, this is one of the few people that I wanted you to know over the course of the semester. I wanted you to know who Christian Anfinsen was. And what he did was he took the fully folded and functional protein, RNase A, which ultimately is a protein that we actually kind of address a couple times throughout the semester. And what he did was he added a bunch of beta-mercaptoethanol, some urea, and he took that fully functional folded and functional, and he converted it, or well, he unfolded it, and so now you have this straight line protein, unfolded and non-functional. And so what he did was, after he got to that point, he titrated away. So he removed BME, the beta-mercaptoethanol, which breaks disulfide bonds, and the urea, and he effectively refolded the protein. And it was again folded and functional. So this is an important discovery. He made an important discovery and important strides in this sort of research. But let's go ahead and look through our answer options. And I apologize for the formatting of this, just because there's so much text that just kind of overwhelmed the screen. Okay, answer option A reads, folding a denatured RNase A into the native active conformation requires the input of energy in the form of heat. Okay, so this one's kind of interesting, and really whenever we think back to what Dr. Anfinsen did, we don't really ever talk about heat. So for this one, what I want to go ahead and do is I'm just going to underline, I'm going to set it aside and say, okay, that's a candidate, but let's see if there's a better answer option. Answer option B reads, native ribonuclease A does not have unique secondary and tertiary structure. Okay, well that's going to be something that's kind of off the table because every protein has a unique secondary and tertiary structure. I mean, there are some common themes and threads to those structures, but that one's going to be removed for that purpose. Answer option C reads, the completely unfolded enzyme with all SS bonds, so disulfide bonds, broken is still enzymatically active. That is not true, because we added that beta-mercaptoethanol that broke all the disulfide bonds. An alternative solution, or an alternative substance that you could use, is dithiothreatol, but whenever you break those, you've ultimately unfolded that protein altogether. Answer option D reads, the enzyme dissolved in water is thermodynamically stable relative to the mixture of amino acids whose residues are contained in RNase A. That seems a little bit kind of wonky, and I mean, I wouldn't even really know where to start with why that one could be right there. So let's go ahead and move on to answer option E, which reads, the primary sequence of RNase is sufficient to determine specific secondary and tertiary structure. Okay, so when you compare, let's go ahead and compare A, D, and E and say which one of these is the best answer option. Well, E shows that the primary sequence, so basically that all those peptide bonds, those covalent bonds that hold all these individual amino acids together, that's sufficient to determine specific secondary and tertiary structure. Well, Dr. Anfinson, he produced a primary structure. He produced an unfolded non-functional protein and refolded it into its necessary or its specific secondary and tertiary structure. So we don't even really have to address answer options A and D again, just because E is such a good answer option. So I'm just going to circle E as my best answer option for that. Okay, question number 8. How does the addition of BPG to hemoglobin impact its P50? Now, so whenever you think about hemoglobin, I want you to think about an oxygen binding curve. And an oxygen binding curve looks a little bit like this in the case of hemoglobin. Now, when it comes to movement of this, we are concerned with its moving to the right, or I'm sorry, moving to the left or moving to the right. Now, if it moves to the right, well, then we have to be concerned with, well, the P50. So what you have to know what a P50 is. This is the PO2 required to reach half saturation of our protein. Okay, now what we see with this is in the presence of BPG, hemoglobin's oxygen binding curve actually moves to the right. And so our oxygen binding curve will look a little bit like that. Now, whenever we see that, what does that mean for our P50? So our P50, our percent saturation, is on our y-axis, 50%, 100% up here, 0 down here. Well, our PO2 is our concentration, basically our oxygen concentration, and that moves from 0 to a larger number. What we see is that the amount of oxygen that is required to get your protein to its P50 has gone up. So the correct answer option is B, the P50 increases. Answer options A, E, and D are basically, well, you can kind of eliminate those right off the bat, and ultimately you just have to know the shift of that curve. If it moves to the right or if it moves to the left, what does that mean for the P50? So if it moves to the right, your P50 has gone up. So that means your protein's affinity for that, that ligand has gone down. All right. Moving on to question number 9. This is a discrete question. This is one that you just have to know this value. Approximately how many amino acids are in one turn of an alpha helix? And the answer to that is simply 3.6. So as you rotate up, there are approximately 3.6 amino acids that complete this movement from here to here. So this is a discrete question. You just have to have this, you had to know this one. Okay, question number 10. A molecule of CO2 binding to the N-termini of hemoglobin is also known as, okay, carbamylation, carboxylification, carbation, carbamation, and finally cartography. Okay, well, cartography that's what Buster Bluth from Arrested Development got one of his advanced degrees in. That's the study of maps. Carboxylification, carbation, carbamation, these are all kind of viable answers. And again, this is like question number 9. You just had to know this information. You had to know this term in order to be able to decipher it. You're not going to be able to deduce it necessarily. Okay, question number 11. CO2 binding to the N-termini of hemoglobin will cause the oxygen binding curve to move to the left or to the right. Now, or I'm sorry, will cause it to move where? Answer option A is nowhere, B is to the right, C is to the left, D is up, or I'm sorry, D is down, E is up. So this again is a question that looks at an oxygen binding curve. And in order to answer this question, you have to know what an oxygen binding curve for hemoglobin looks like. So basically there's your starter. Now the question is, where does your oxygen binding curve go? Answer option A of nowhere is off the table. D down and E up, those are both off the table. The question is it moving to the right or to the left? And we looked at a slide that talked about the Bohr effect. and that was with studies of O2 binding and pH. And from a physiological pH, what we saw was that as our pH goes down, our oxygen binding curve, O2 curve, moves right. Okay. Now, when CO2 binds, then pH goes down. So hydrogen ion concentration goes up. When the pH goes down and it gets more acidic, what we're going to see is this oxygen binding curve move to the right. Okay. Now, question number 12. Our second to last question for this video is, which of the amino acids is capable of forming a disulfide bond? This is something you just have to know which amino acids have sulfur in them. Serine has a hydroxide group, methionine has sulfur, cysteine has sulfur, alanine, no dice, aspartic acid, that's our carboxylic acid. So we are down to methionine and cysteine, and this is just a matter of, do you know your structure for methionine, which is going to have a sulfur followed by a CH3, or cysteine, which is a sulfhydryl group. So cysteine is a residue that's capable of forming the SS bonds that basically, so within a polypeptide strand, the cysteine residue can form those bonds. Question number 13. Select the answer that has the incorrect pairing of name and three-letter code. This is a discrete question. What's the three-letter code for a given amino acid? So we've got name and our three-letter code. You have a total of 20 amino acids that you have to know. Many of them are quite simple because it's the first three letters, but it's not always that case. Serine, SER, that is one case, where SER are the first three letters, and that's the three-letter code. Tryptophan, ultimately this is our answer that we want to select, so I'm going to skip that. Threonine, that is the correct three-letter code. Cysteine, CYS, is the correct three-letter code. Glycine, GLY, is the correct three-letter code. And sorry, serine, SER, is the three-letter code. So ultimately we're left with tryptophan, TRY. Well, tryptophan is TRP, so not TRY. So answer option B is the correct answer there. Alright, I hope this video is helpful. Again, I'm going to go ahead and follow up with some more videos after a little while. Thank you.